Boom. Hello and welcome back to Calculus 1. This is going to be chain rule part 2. So we talked about the chain rule last time. We had the formula. We said that the chain rule is the way to take the derivative of composite functions. So we have g of x, as you can see, plugged into f of x, and then we take the derivative of the, what we say, outer function, f of x, which is with the g plugged in, and then chain it with the derivative g of x. So the example of that was x to the 5. That's a bad example. But example, sine 4x. So sine x is the outer function. We take the derivative of sine, which is cosine. So this is that first part where you take the derivative of the outer function. And then times g prime. Well, g was 4x, so the derivative of that is 4. And that will be the chain. We put that 4 now in front to make everything look good. And then I connected that to the formula that you guys were supposed to, good morning, memorize before, but now you know why is it the way it is, because of that the chain rule. We did more examples of that, but we have to do much more. I promised about 90%, 95% of all derivatives you ever take across courses, which is Calc 2 and Calc 3 and differential equations, are going to be chain rule. And that's why this is so important. So let's say we have the derivative of, and now I can say e to the x squared plus x minus 3. So we are looking at this and we can clearly see that this is composed of e to the x and then the exponent, which is x squared plus x minus 3. So outer function would be e to the x. And the inner function g, which is plugged into e to the x, is x squared plus x minus 3. So now, what do? We take the derivative of the outer function first. Now derivative of e to the x is itself, and we have to have g still plugged in. So we get to copy the entire function there. And then times the derivative of the inner function, which is the one that is in the exponent, and that's 2x plus 1. The derivative of x squared is 2x, and the derivative of positive x is positive 1. So that's it. We're done. That's that. And now, this is just taking the derivative. What are the future problems? Future problems are find the tangent line and you plug in x to get slope. Or set it equal to 0 to find x values. We will call that critical points in chapter 4. So there's going to be an upgrade on every single problem we do in chapter 3. Chapter 3 is teaching us how to take derivatives of more complicated situations so that we don't have to suffer with the limit. That's the purpose of chapter 3. Chapter 4 is application of derivatives. So chapter 4 will tell us what to do with this stuff. So what you see in chapter 3 is the first step of every problem of chapter 4 and later, obviously. So this is just a method to take the derivative and then move on. Now, let's see what we do with, say, square root of sine cubed of, let's say, 5x. Now, hopefully, as a notation, you guys know that, let's see, how about some purple over here, that sine squared x is actually sine x squared as a notation. You have the same thing for ln. So ln squared x is parentheses of ln x, everything squared. So this notation helps us to understand that this 3 and the square root are actually in one fractional exponent. So we get to rewrite this as the derivative of, and then I get to write in parentheses sine 5x, and what exponent? 3/2. So the square root is giving me half exponent, and the 3 is giving me cube. So I have, so first I write sine 5x everything cubed, and that's the square root. So then that square root becomes a half, and that's what we have. Good. Now we see that we have how many layers of functions here? 2, 3, 4, 5, 3. Because we have the outer layer x to the 3/2. Then we have one step in, which is sine x. And then we have all the way in 5x. So this is one that has 3 layers that we need to worry about. All right, well, let's start with the outer layer. The derivative of x to the 3/2. It must be 3/2 x to the 1/2. Now observe what I did. I didn't write the x. I put the parenthesis because the whatever is in parentheses here will go there, which is sine 5x. So that's the way I learned it. It was visual for me to say, oh, this is 3/2 x to the 1/2, but I will not write x. I will write whatever the parenthesis tells me to write. So I just put this sine of 5x in here times the derivative of the inside, so the derivative of this part, and the derivative of sine is cosine, so cosine 5x, and then again the derivative of the inside, and the derivative of the inside is 5. Now someone might say, well, how about times 0 now, because the derivative of 5 is 0, because we can go on. Well, we can't, because we already exhausted the number of chains. If you pay attention here, 1, 2, 3. Pay attention here, 1, 2, 3. You're done, right? It has to match the number of functions, has to match the number of derivative parts. So that's the end. Now we have to clean this up, make it look better. So this is 15/2 of cosine 5x times the square root of sine 5x. It's okay, you can leave it that way. And that will be it. All right, so the derivative of tangent of the square root of x squared plus 1. Have fun. I'll try to leave the upper example so you can refer to it should you need to. Okay, let's take a look. What is the number of functions that we have? 3. What's the outer layer? Tangent x, very good. How about one inside? Root x, very good. And how about the one all the way? Very good. So I better have 3 parts in the derivative. What's the derivative of tangent? Secant squared. So we have a secant squared of square root of x squared plus 1. Good. Times the derivative of square root of x, 1 over 2 root x, but we have to put x squared plus 1. Times, and the derivative of the inside is 2x plus 0, so just 2x. Now we see that this 2 dies, and what are we left with? We're left with x secant squared square root of x squared plus 1 divided the square root of x squared plus 1. Can we just cancel these and be done? Can we? It's not no, it's hell no. There's a difference between the two. Right? It's hell no, you can't. This one is the argument of secant, and this one is a factor, so you can't cancel them. Think of this one as being buried by the secant, and it's buried also by the square too. So this is This is like the secant of square root of x squared plus 1, everything squared. So you see that to get to it, you first have to get rid of the secant square, then you have to get rid of the secant, and then you have it free. And that's a lot of work. So that will be the derivative. Now, is this enough of playing in a sandbox with little plastic shovels and buckets? All right, let's see some serious stuff. What can we do to make life more annoying, more complicated, for absolutely no reason? We are going to combine this chain rule with product rule and the quotient rule in all possible ways. And we are going, in the process of that, we're going to define something that's called the annoyance, right? It's not going to be hard. There's nothing hard. You have 3 formulas, all right? So don't label it hard. It's annoying, right? There's difference between the 2 concepts. So we have the derivative of e to the 2x times sine 5x. So, there you go. Now you're looking at this thing and you say, well, great. It's not e to the x. It's not basic. And it's not sine x. It's not basic. So those are chain rules. But then they're multiplied, which means the product rule. Now it's important to figure out, is this a product within the chain, or is it a chain within the product? And this is what we have here, is chain in product, chain within product. And I'll write that. Well, in this case, chains, right, because we have 2 of those. Chain within the product. And I will put this red times in between the 2 functions so we can see that. So what's happening? Well, I have to use my formula UV. The product rule was UV prime plus VU prime. All right, let's go. Copy the first, e to the 2x, times the derivative of the second. Well, great, that's a chain rule now. So what is that? Derivative of sine is cosine 5x, and then the derivative of 5x is, so 5 cosine 5x, good. Plus, copy the second, which is sine 5x, times the derivative of the first. And what's the derivative of e to the 2x? It's e to the 2x times the chain of 2. So you can put 2 in front. Now when you look at these, you see that you have e to the x common. So you kick that out, common factor, and you are left with 5 cosine 5x plus 2 sine 2x. You have to do this because the next step is equal to 0 and, you know, doing other stuff. That's what I said, please pay attention. It says 5x, look. All right, thank you. So in this problem, we had the product rule, and each individual piece had the chain rule inside. Let me give you one of the solutions for differential equations that you have to differentiate twice to check if it's a valid solution. So your answer for the problem would be y equals, but we are going to say take the derivative. of e to the 2t times, and over here we'll have, let's say, 1/2 cosine 3t plus 5/2 sine 3t. So this is what you see there is a standard wave solution for the second order differential equation that has complex roots on a characteristic equation. Now you're going to learn that when you get there, right? But the way to solve and way to do all of this stuff. But the last step is to check that this is actually correct. Now, yeah, it's easy when you have an equation like this and you get that x is equal to 2, right? Well, yeah, you plug in 2 for x, 2 plus 3 is 5. Differential equations work the same way, except the answers are not x equals 2 numbers. Answers are entire functions. And then if your differential equation was x double prime plus 3x prime, right? You see you have to plug in it's not x prime, y double prime, y prime, blah, blah, blah. You see you have to plug in the second derivative of the function. And over here you have to plug in the first derivative of the function. So it's not just, plug in like in these equations, plug in number. So you have to be able to take these types of derivatives, which I'm talking about today, the more complicated one. Well, now when you look at this stuff, yeah, it's still a product rule, right? And you definitely have chain rules to worry about, because each one of these steps, right? So, again, is it hard? No, it's not hard. Is it annoying? Sure, I'll give you that. This is the part when you turn your notebook sideways, right? So you can actually fit all of this stuff. Because it is still going to be u, and the entire parentheses v, and you have u times v, where you copy the first, e to the 2t, times the derivative of the second. Great. Chain rules are going to start kicking in because of the 3t in the thing. Now the good thing is that that 3 just goes in front. So the derivative of cosine is negative sine. So what do I have? I have negative 3/2 sine 3t. Derivative of sine is cosine, so plus 15/2 cosine 3t. Let me just, for some reason it's giving me attitude while I'm writing, so there we go. Hopefully it's fixed. So that's the copy the first, derivative of the second, plus copy the second. Well, that's 1/2 cosine 3t plus 5/2 sine 3t, and now I need to take the derivative of the first. Now we know that that's 2e to the 2t, because it is just the it's exponential function. You can also remember, right, a e to the at if that makes you happy, but the chain rule takes care of it, so you don't have to. So now what? Well, now factor everything and then add like terms, because you have sine 3t and sine 3t. You will distribute the 2. Do not cancel the fractions because you need common denominator to add, so double the numerators. So what do I have? When I factor out e to the 2t, the rest stays in parentheses, so negative 3/2 sine 3t plus 15/2 cosine 3t, and now plus 2/2 cosine 3t plus 10/2 sine 3t. Again, I did not cancel the halves with the 2. I multiplied the numerators because I need common denominators between the two. So now this guy and this guy are common, and this guy and this guy are common, so I can add them up. So what I have is e to the 2t, And now you take a look at this. So sine and a sine. So 10 minus 3 is 7 halves. Sine 3t. And then 15 plus 2 is 17 halves. Cosine 3t. And that would be the answer. And what do you do then? Again, you take another derivative to find the second derivative, because your differential equation was y double prime plus 3y prime minus, I don't know, 10y equals to 0. So you have to plug in second derivative here. This thing, whole thing, goes here. The original function, which is all the way on top, goes there. And then you still have to take derivative of this for the first one. And then you have these 2 multiplied by 3 and negative 10, and make sure that everything cancels to 0 to show that your answer, which was whatever is in this parenthesis here, that your answer was correct. It's a little bit more involved than x plus 2 is 5. Still an equation. It works. So practice these things if you are going forward. The chain rule will be back in all of its glory, right? In every math course you take after Calc 1. It has to. So, yeah. Next. Let's have the derivative of cotangent of x squared plus 1 divided by e to the x. That's a beautiful problem. We'll try to wrestle with this for some time. Talk to people around you. If you can stand them, obviously. So what do we have over here? Anyone? Chain within product, product within quotient. What do we have? Problems like this, believe it or not, are a huge issue for a lot of students. Quotient within chain. Good. Is there times in between over here? Hell no. Right? This is inside of cotangent. COT by itself means nothing. You must have something in this box in order for COT to have a meaning as a cotangent. So you can't just have a COT and then times a function. So this is definitely quotient within chain. Chain is the main one because you are taking the derivative of a cotangent with some other function plugged in. Now the problem is that the function that is plugged in is a quotient rule. So this is the quotient within chain. So we start by working the chain first. Chain rule said the derivative of cotangent is, anyone? Negative cosecant squared. And then we have x squared plus 1 over e to the x. Times, and now when we are doing the derivative of the inside, this is where the quotient rule kicks in. So we have e to the 2x, e to the x times the derivative of top, which is 2x, minus copy the top, which is x squared plus 1, times the derivative of e to the x, which is e to the x. Now the whole bunch of stuff, not the whole bunch of stuff, but at least e to the x cancels. The denominator here is e to the x times e to the x. So one of the e to the x's will cancel. So I have e to the x gone, e to the x, and then the square goes away because that's like taking out one of the e to the x's and the second one stays. So what's left? Negative cosecant square of x squared plus 1 over e to the x times, and now I have negative x squared negative x squared plus 2x minus 1 divided by e to the x. What I'm going to do is I'm going to take this negative 1 in front and multiply into numerator and change all of the signs and put it in front. So now I have x squared minus 2x plus 1 over e to the x times the cosecant squared of x squared plus 1 over e to the x. And that would be it. Lots of fun, as you can see, depending on the way you define fun. So it's either this or the limit. It'll probably take a year to get the limit done, but that's okay. Let's take a look at the derivative of sine 3x divided by the square root of x squared plus 1. So now we have what? What do we have? Chain inside the quotient. Very good. All right. So, line. Denominator squared. Well, that's just x squared plus 1. Copy denominator as is. Times the derivative of the numerator, which is 3 cosine 3x. That's the chain rule. Minus, and now we have to take the derivative of the denominator. Well, that's what? Derivative of this guy. So we have 1 over 2 square root of x squared plus 1 times the derivative of the inside, which is 2x. And we copy the sine 3x. So now the 2 and 2 cancel. Now when I write this out, there will be some simplifying to do. We have a square root of x squared plus 1. There's 3 in front. And the cosine 3x minus x over square root of x squared plus 1. And then we have sine 3x. Everything divided by x squared plus 1. Now what I can do to make this better is to multiply by square root of x squared plus 1. Now in denominator this gains an exponent to 3/2, right? Because you have x squared plus 1 raised to the first power times x squared plus 1 raised to the 1/2 power. 1 plus 1/2 is 3/2. So we have 3/2 exponent in the denominator. In the numerator, this works miracles. Look at this. Square root times the square root becomes 1. So this is 3x squared plus 1 cosine 3x minus, and over here they cancel. So I just have x sine 3x. And I eliminated the double fraction, which is good. And this is it. Now you go equals 0 and you keep solving this thing, but we don't have to anymore. And that would be this second part of the chain rule. You can take the second derivative, the third derivative, the fourth derivative, and they progressively get worse as you go from layer to layer. They have to. And we already did an example of the tangent line. We'll do next Saturday more examples of the tangent line utilizing the chain rule. So as I said, next Saturday at 9 a.m. we are going to go through all different types of chain rule, all different types of product rule and quotient rule, and then all of that stuff within tangent lines and so on. So let's take a break, and then when we come back, more derivatives. Next section.